It's really a thrill to be back here, to be invited, to be part of this celebration. You know, it's like one great big family reunion. And I find that thought both comforting and at the same time terrifying. Because if you mess up, you know you're going to hear about it again and again and again. I do have one safety net, though. My multi-talented friend, Natalie Artwork, has loaned me some of her beautiful artwork that she's done from her observations and walks in Hubbard Brook Valley. So if I'm totally dying on here, I have some really nice artwork that Natalie has provided that's really quite beautiful to look at. So thanks, Nat. So here's just a brief outline of my talk. I want to provide some of my perspective of Hubbard Brook, and then quickly go to Herb's idea of creeping degradation and how that informs how I think about what's going on in the forest here at Hubbard Brook. Look at the long-term evidence from the forest, from the tree data, and then briefly at the end talk about some ideas of how you can support resilience and how this feeds into the future. So I share a birthday with Hubbard Brook. I turned 50 this year, and it's a good time to think about, to reflect back on what's going on with your life and with the study. And like every endeavor, it's always good to get some feedback. So my most valuable feedback came from my teenage son. He was kind of listening to me as I was telling him about this trip, and I was pretty nervous about this talk, and he was kind of doing the teenage, oh, I gotta listen to Dad, it makes him feel good, but this is really boring, Dad. Until I mentioned the topic of my talk. I said, creeping degradation. And he says, creeping degradation? Dad, that's an idea you can talk about from personal experience. Now, fortunately, Hubbard Brook, the ecosystem, and Hubbard Brook, the institution, is not bound by the same rules that we organisms are. We're not fated to senescent to senility right away. There's actually mechanisms for renewal and rejuvenation that gives us some hope. And when I talk about Hubbard Brook, the institution, I'm not talking about the various organizing bodies that run the place, but really it's my term for the idea of Hubbard Brook, the foundations of Hubbard Brook that Gene so eloquently described that really are important. And I'll touch on both aspects, Hubbard Brook, the ecosystem, and Hubbard Brook, the institution. I first heard of this idea of creeping degradation in 1988. I was taking Herb Borman's ecosystem ecology course at Yale. I think it was the last time he taught it in 1988. And so there was this extra energy in the room that year. Every seminar, people were prepared, and Herb really was at the top of his game. And one of the papers we had, he had drafted this paper that ultimately ended up in a book with George Woodwell about the earth in transition and the challenge of biotic impoverishment. And he had us read this paper about creeping degradation. And it's forever sort of stuck in my head on how Herb thought about the forest worked and how thinking about how you can manage it, how you can understand it, how you can do something to make it better. Herb's essential insight into that was that he understood trees. And it's important to understand his idea of creeping degradation to understand trees. Most trees are extraordinarily conservative. They're at the top of the plant evolution apex for two main reasons. They get really big and they live a long time. And they dominate the most productive habitats on Earth because they do that better than any other plants. And if you have a life history strategy that needs to be big and needs to live a long time, you're extraordinarily conservative. So the typical trees, certainly these trees here, the dominant trees in Hubbard Brook Valley, beech, sugar maple, and yellow birch, are very conservative. They're the canopy dominants. They probably have 3 times the biomechanical strength they need to withstand the typical stresses and strains. They're probably doubly redundant in terms of their plumbing. And they store vast reserves of carbon for emergencies. For example, a frequent occurrence that occurs in these woods is an insect outbreak that will defoliate all of the leaves from these canopy trees. And once that outbreak is over with, in a few short weeks, the tree will reflush and reproduce all of that leaf matter. So how many of us have an emergency reserve that we could automatically replace all our productive assets in the same system? So they're very conservative. The result of that is that trees and forests change very slowly. And here you see this collaboration that Gene was talking about, because Herb thought of it as kind of like a buffered system, and where the trees can take a lot of stress. They respond to these chronic stresses like air pollution, like climate change, by eating into their reserves. So you don't see a change. Kind of like adding acid to a buffered solution. You don't see a change. And oftentimes when you do see a change, it's a very quick change. And by that point, and his point was, that it's too late. So we've got to remember, when this paper was being written, the big threat to the world's forests was more deforestation, these catastrophic losses. And yet Herb was worried about the next challenge, thinking ahead about this creeping degradation and how what humans are doing has this slow moving. The way he conceived of it, and this is from his paper, is that you're in this place right here that you can take a lot of chronic disturbance and see very little change into the system until you get to this point where it changes very rapidly and you see a state change from a forest-dominated area to a shrub-dominated area, or some ecosystem function from high productivity to lower productivity, or from nitrogen retention to nitrogen leaking. Some important change, and it's very quick. And that makes it hard, because you can't see it coming, and then how do you respond? Now, again, like a lot of what happened at Hubbard Brook, Borman was ahead of his time, and this idea has been developed over the last 20 years by people like Holling and Gunderson and Folk and Carpenter. And in a good review, this kind of shows what you're thinking about. We would hope that ecosystem state, if it changed slowly as conditions change, you can respond. But this is really what Herb was talking about with his creeping degradation, and it's still very much part of the thinking, is that you don't see any change in the state, and then you see a very rapid change. We sometimes might call this a tipping point. And this third one here is a little bit more complicated, where you might be flipping back and forth. And it doesn't so much apply to forests. But our forests here kind of at this tipping point to a lower productivity state. And again, a way to think about this and a way to prevent this is this idea of building resilience. What Herb would call would be improving the buffering capacity of your system. And the basic idea, and I don't want to get into these cup and ball diagrams, can be quite complicated, but some ecosystems have high resilience, and it's hard to move that ball out. So resilience is the capacity of an ecosystem to maintain its essential structure and function, and usually it's in light of some kind of novel stressor or some kind of forcing agent. And then other ecosystems have low resilience, and that ball can move around pretty easy. But the goal in terms of management, of understanding how these systems work, would be to improve somehow this high resilience. If you're getting near this top, first you need to detect it, and perhaps you can do something to push it back down in there. And that's kind of the challenge. So what does the trees say about what's going on here? What is the evidence from the trees if we think about creeping degradation and the resilience of the forest ecosystem from the vegetation perspective? Now this is right from the book, the second most cited book in Hubbard Brook, Borman and Likens, 1979. And this really was the conception back 50 years ago when they were thinking about Hubbard Brook, that the stressors we had here were these catastrophic losses, either naturally in terms of like the 1938 hurricane that came through the area and knocked down lots of the trees, or logging events, both in the 1900s and back in 1965. And these have catastrophic loss of biomass. And the idea, the concept that you go down to zero, the living biomass goes down to zero, and then it recovers through time. It grows fast, it reaches a peak, and it settles down to this shifting mosaic steady state. Now the assumption here is that nothing else happens after this catastrophic loss. There's no other stressors intervene. And by all our experiences up to that time, this is how we thought the northern hardwood forest worked. And in fact, there was good evidence to think that the northern hardwood forest was a very resilient ecosystem, that it maintained its structure and function after catastrophic loss, and that it came back. It recovered. Now this is what I like to call the Sycamore graph. This is what I imagine. Whenever I think of Tom, I think a lot of things when I think of Tom. Like, for example, I love this picture that Ellen Denny shared, is that Tom was the original sustainability. He really was into it way ahead of everybody else. He would reuse everything. And this is one right here, his ubiquitous IBM cards. He had boxes of these that he used as note cards from throughout his entire career. They were useful to about, 1975? And then we started stripping the tape. So we had just boxes of this, and he would reuse these. Of course, we know that Tom's real ethic of wasn't so much reuse, was never throw anything away. Yeah. The other part I like is that, Tom, I always thought Tom was a forest ecologist, and his dissertation was on vegetation, and that was his expertise, but he had a huge fondness for dirt. And this hat, or versions of this hat, I don't know how many he had, but he always had a dirt hat going on. And of course, this is his multi-wear. This is for the field. This is at a conference. Doesn't matter where he was. It's pretty much the same outfit. I think he dressed up a little bit with the chamois shirt here. But this graph represents really 40 years of very careful long-term measurements. Tom came on board. He wasn't here for the 1965 measurement, but he led every other measurement of the total biomass on watershed 6, which is the reference watershed, for over 40 years. And he didn't just go and measure it, but he carefully and constantly refined it, improved it, and I think most importantly, really a hallmark of what we do at Hubbard Brook, is that he validated these equations to make sure he was doing it right. And this long-term data, as Jean was pointing out, is incredibly valuable because he proved through his work, the long-term work that he led here, that the forests on watershed 6 had stopped growing. They weren't doing what was expected back in 1970, and that they had fallen far short of the total biomass. We expected somewhere about 500 megatons per hectare or tons per hectare, and they leveled off at about 250. And not only did they not make that magnitude, but they stopped growing a lot earlier, a lot sooner. And indeed, more recently, they have declined going forward. So we have this decline in forest growth. And the question is, what's going on? What's causing this? I just want to step back and think about Hubbard Brook, the institution, and again, the hallmark is the long-term record. And what it takes to do and create this long-term record. When you're studying an ecosystem where the primary organisms live much longer than a human time span. And I think there's a lot of researchers and studies out there that buy into the principle of long-term data. It's an easy principle to buy into. It's an attractive principle. But as we learned here at Hubbard Brook, it's incredibly hard to do. It is not the glamorous side of Hubbard Brook science. You can talk to Don Busso, you can talk to Amy Bailey about the non-glamorous side of long-term research. And Tom did this incredibly well and for an incredibly long period of time. And I totally underestimated the amount of effort, both intellectual effort and just tedium effort involved when I came back in 2004 and started working with it. The other challenge to this as well is that no matter how good your data is archived and explained, and in fact Hubbard Brook with Mary Martin's work has a really good system of archiving our data, this active handoff between scientists is key. And it's not easy. I knew when I came here, despite being sort of a student and a colleague and a friend of Tom's, that I was taking over his research and I was messing with his baby. And so we worked together for 4 years making this active transfer. And I learned so much, and at the same time, I captured all the stuff that wasn't there. And this active transfer is tricky. And I know part of my obligation going forward is to find my successor. Now, it's not going to be this character because he's quipping about old man dad. But he might be a little bit, he's older now, but he's still too young. But it might be somebody from the ice cream stand, the Purple Elephant ice cream stand. Again, another crop of researchers who come here as undergraduates or grad students and spend their summer doing their research in Hubbard Brook. And I can give you the coordinates of the Purple Elephant ice cream stand in the woods if you want to find it. The bird is if you're out there. I don't know if you've run into it yet. So why did the forest stop growing? Well, I think one of them, of course, is that unanticipated events happened. We didn't have this, it wasn't on the radar screen. We discovered acid rain here at Hubbard Brook. And so initially we thought the Hubbard Brook Valley was affected by logging and hurricanes. But then we found out we also had air pollution. And of course now we have climate change. And then we also had some invasive species coming in, an exotic insect that led to disease of one of the dominants. We also had some rare events. If you keep studying, even rare events, if you keep studying long enough, you will find them and be able to measure them, which is of great value. So we had the 1998 ice storm, which we don't think was a human-generated event, but it certainly was rare. And just this year, we had one of these thunderstorm microbursts that, again, pretty common but very localized, sort of hit the south-facing slope just west of watershed 6 in the valley. And they changed things. This idea that only one thing happens and then the forest recovers, well, there's been a lot more going on. So what I've done is I've charted these on the timeline. So this, again, is the Sycamore graph, where I have year here. I have above ground live biomass from the initial measurement in 1965 to last year's measurement in 2012. Again, from watershed 6, which is the control or the reference watershed, and just started charting the events that happened. Back in the early 1960s, we were realizing that the red spruce were declining. They dominate the top part of the mountain, again, related to acid rain. We see sometime in the late 70s, the mid-70s, we had the peak SO4 deposition. So the peak of the acid rain input was there. By 1982, we had beach bark disease as being confirmed in Hubbard Brook Valley. Earlier in the 1990s, we thought there was too much nitrogen coming in here, and so we're getting saturated in terms of nitrogen. That has huge implications for forest growth. We noted a sugar maple decline, again, probably related to acid rain and calcium deficiency. We had the 1998 ice storm. We had the ongoing paper burst decline, and in 2013, we had this microburst. So there's a lot going on. Some of it natural and rare, some of it clearly human-generated. And of course, at the bottom here, we have warming temperatures, and we also have increasing precipitation going on. So what started off as the 1938 hurricane as being the initiator, we have all these other events. And in the future can be scary as well. We have three really aggressive invasive insects sort of literally on our borders. We have the emerald ash borer, hemlock woolly adelgid, and the Asian longhorn beetle. And all of these, we have trees susceptible to these pests in our watersheds. For example, I've done some work with the hemlock woolly adelgid south in Pennsylvania and New Jersey. Again, it's an adelgid. It's a phloem sucker. It gets on the leaves and just basically sucks the carbon out of the tree. You can see this woolly mass on the hemlocks. And there really is no response. There's no inherent resistance in the species to this pest. And this is work showing survival from 3 sites down in the Delaware Water Gap. And again, this is a 20-year record. And again, while there's variation from relatively little death to only 10%, to in some areas 60% of the trees have died. Survival is down to 0.4. And again, the timing might matter, it might change, but the results are pretty much the same. There's going to be a huge, when it arrives, there's no response. So how do we plan for that? How do we build in any kind of resilience to these kinds of events? So how do we support resilience? Again, resilience being this capacity to sustain function and processes in light of novel stressors. And I think we have a very sparse toolkit, and that's really the challenge for the future. Now, one way, and the best way, is to remove the stressor. And you've already seen both of these graphs. Gene made both of these points, in that we've been extraordinarily successful in limiting acid rain. Both sulfate and nitrate NOx contributions to Hubbard Brook from our source areas have declined since 1970 to the present. And again, from 1970 to the present, they've declined. A great success, a policy success. But as Gene pointed out, we also see the conductivity in the rainwater and stream water has also declined, to the point now where it's almost too clean, where the trajectory is toward this distilled water, which also is a risk in and of itself. But in some ways, we have removed the stress. The other alternative, of course, is to protect what you have. So there's active monitoring programs going on to monitor the arrival of the adelgid. I think the Forest Service, with Ian's work, has pheromone collectors to look for the emerald ash borer. So we're trying to see when it comes and anticipate them coming so we can respond early in the process. Another idea, and again, something that a place like Hubbard Brook thinks about, they think big, is that if humans broke it, they should be able to fix it. And this is the idea, again, Gene alluded to it, where, again, 3 decades of acid rain had removed the calcium from the soil, calcium being sort of a major plant nutrient. And so the scientists at Hubbard Brook, even before I came back, had devised a study. Charlie Driscoll was the leader of this study, along with Chris Johnson and Joel Bloom. And they decided they would add a slow-releasing calcium silicate material to watershed 1, a whole watershed ecosystem, and replace that lost calcium. And let's see what happens. It's a big-scale project over the long term, and we finally the forest took 15 years to respond. So here, they take pre-measurements in watershed 1, which is in the red, and blue is watershed 6. Again, it's the same graph, above-ground live tree biomass in megagrams per hectare, and again, it's the trajectory through time. And what we can see is that before the treatments, watershed 1 and 6, like a paired watershed should be, they're very similar in terms of their total above-ground live tree biomass. Now, of course, nature intervened, and we had the 1999, they put the calcium on there. Of course, in 1998, we had that ice storm. So it kind of put a little ring in there. But you saw that this big decline in watershed 6, probably related to the ice storm. In watershed 1, the decline wasn't nearly as bad. That the trees that were injured were able to respond and heal their wounds and grow faster. And then, of course, by 10 years, 12 years after the study, there was a big increase in recovery of watershed 1 where the calcium was added. So this is a very interventionist way of building, in some ways, resilience. Because we added the calcium, and the effect of another disturbance, the ice storm, was a lot less in the calcium-treated watershed than in the one that didn't have it. And so in some ways, we were able to build in some of this resilience back to the system, and so the impact was buffered, if you will. Now, of course, there's tons of challenges to this kind of work. There's a resistance to major interventions. You need to understand the system very well. We didn't put calcium on there just willy-nilly. It was probably 20 years of very careful research going forward. What's the next step? As I was thinking about Hubbard Brook, this idea, this poem by Lord Tennyson, Ulysses, came to mind. This is the famous poem. Everybody knows that the heroic ending, to strive, to seek, to find, and not to yield. But the poem is more complicated than that. And in fact, the context is that Ulysses, or Odysseus in the Greek, is returning back to his kingdom of Ithaca after 20 years of adventures with his crew. He'd gone off to the Trojan Wars, and then on the way back, of course, he ran into some events on his voyage home that we all know about. And he was coming back into Ithaca, and he didn't want to go home. That he enjoyed the adventure too much. He didn't want to return to the humdrum life of being a king and ruling a kingdom. He would much rather stay out and continue to learn and to explore, even though he's middle-aged. He describes his crew at one point as men with free hearts and free foreheads, and still has this desire to learn. They still want to go out. He doesn't want to return. His son can take over. His wife hasn't seen him in 2 decades. He wants to keep doing it. And I think that, as Hubbard Brook faces middle age, we should take the same thing. And this great spirit, yearning and desire to follow knowledge like a sinking star beyond the utmost bound of human thought. That really is what Hubbard Brook, the institution. And I think, from my perspective, that the genius of Hubbard Brook, that this Hubbard Brook ecosystem study that Borman and Likens and Pierce and Johnson found is not in the small watershed concept, is not in the discovery of acid rain or all the other specific scientific insights they found, but is in building this community of scholars we see here who are committed through the generations to the idea that we need to understand nature well enough so we can try and get humans live sustainably within it. Thank you.
We have time for 1 or 2 quick questions for John. Anybody have any?
Are there any known effective solutions to those 3 bug infestations, or do we just know they've arrived in wheat?
Yeah,
repeat the question.
Okay, so the question was, are there any known solutions to the 3 invasive insects on the horizon? And the answer is no. There's been a bunch of biological control agents released for hemlock woolly delegate that have been relatively ineffective. And so there really are no control agents on the horizon. They're still looking for them. The best is biological control, but they're very difficult to get. So far, no.
Yeah, we can see how we got here by connecting the dots going backwards. It's something that Steve Jobs said. And it clearly has produced outstanding results. But it seems to me, with the challenge of climate change, with a 10 or 15-year option here before we really do fall off the table, does Hubbard Brook have to take a different approach to deal with this real crisis challenge that is on such a vast scale that we could easily lose it as we move forward?
So the question was, with climate change, cliff looming, where there's going to be more radical changes than we've already reserved in 10 to 20 years, does Hubbard Brook have to take a radically different approach to how they do science? And I think the question you raised a really good question, because one of the challenges of a long-term ecosystem study is that you're always looking at the past record and the investments you have there and certain topics of study, and then what the future. And we argue about this and wrestle with this question all the time on where do you put your chips. Do you take some radical approach to Hubbard Brook Because whenever you do something, you're not doing something else. And I think that's a good question. And I think part of this idea of creeping degradation is that you oftentimes don't act until it's a crisis. But if you knew the crisis was coming with some certainty, then you could respond. And here, we're talking about doing some other experiments that would try and look at that. But it's really, when you think about it, what would you do? You take some wholesale intervention of Hardwood Valley to try and build resilience to climate change? It would be difficult. Think of exactly what would be the best big experiment to do. But it's a good question.
So John will be around, so certainly if you have questions for him, grab him at lunch or after lunch in the break, and he's given us a lot of provocative thoughts about what's going to happen here in the forest moving forward.